You know, usually when we think about turning off a machine, it's pretty binary. Like you flip a switch, the noise stops, and bam, you're safe to open it up.
Right, that's how we're used to things working.
But in the silent world of EV safety, relying on that assumption can be, well, lethal. So today we're doing a deep dive into the research of electromobility trainer Rolandus Rundeika to understand a really rigorous safety sequence called dead working.
Yeah, and we're going to unpack the actual mindset required to safely handle these high-voltage vehicles.
I mean, just starting off, the term dead working sounds a bit like a zombie movie.
It really does, but it just means the vehicle's traction voltage system is completely isolated and secured. That's often referred to as, voltage class B, the high-voltage architecture that actually propels the car.
Right. It doesn't mean the battery chemistry itself just vanishes, obviously.
No, not at all.
But I do want to push back on this a little bit. Isn't powering down an EV ultimately just like turning off a regular internal combustion engine? Like, you pull the key, cut the power, and the danger stops.
Well, see, that specific logic is exactly what gets technicians hurt. Rolandus uses this really great analogy to explain why. So imagine a standard gas engine, right?
Okay, I'm picturing it.
But it has a massive, incredibly heavy steel flywheel attached to it. When you cut the fuel supply and turn off the ignition, that giant flywheel doesn't just instantly stop spinning.
Oh, right, because it carries all that mechanical momentum. I mean, you wouldn't just reach your hands in there while it's still rotating?
Exactly. And in an EV, the electrical capacitors hold potential exactly like that flywheel holds momentum. Even after the vehicle is technically shut off, that residual electrical charge is still physically present in the system.
Because the electrons are just waiting to equalize.
Right. You have to treat the system as entirely live until you manually verify that the metaphorical flywheel has completely stopped.
So if that residual energy is just lingering there, pulling a plug isn't enough, you'd need a physical guarantee that the power can't accidentally bridge back before you start wrenching.
Yeah, which is why the industry relies on a really strict 5-step sequence. You can't just jump in.
So what's step one?
First, you disconnect external sources, like your charging cables. Then second, you turn off the vehicle's internal system. But step 3 is the crucial pivot here.
Okay, what is it?
You have to verify the total absence of hazardous voltage, and you do this using physical measuring tools.
Oh, because you have to prove the system is actually dead before moving to step 4.
Exactly. Step 4 is physically disconnecting the internal battery sources. If you skip step 3, you're basically putting your hands directly into a live circuit.
Wow. And then what's the final step?
Step 5 is securing the vehicle against reconnection using LOTO, or lockout tagout.
Wait, so applying physical padlocks and personal warning tags to the vehicle?
Yeah, you have to. Because if you skip this, low-voltage systems could automatically fire up a contactor, which is basically a heavy-duty electrical switch, and that can silently flood the system with lethal voltage.
Right, while you're elbow deep in the engine bay. That is terrifying.
It really is. But even knowing those steps perfectly, human psychology kind of gets in the way.
Right, there's this crazy story in our sources from a training simulation.
Oh, yeah, the TVS-RIG story.
Yeah, students were working on a TVS-RIG, which is a specialized test rig used to safely simulate high-voltage systems, and they measured the rig, saw a reading of 600 volts DC on the screen.
And inexplicably accepted it as okay.
Right. How does that even happen?
Well, they saw the number on the screen, and they just mentally checked a box that they had performed the measurement step.
So they were just on autopilot.
Exactly. They were ready to move on. They completely missed the context of the data. It was only after the trainer stopped the simulation and really interrogated them about what that number actually meant that they realized they were staring at a lethal hazard.
So we've seen how going on autopilot can cause you to misread a 600-volt measurement. But ironically, the moment technicians are actually most vulnerable to that. Complacency isn't in the middle of a complex diagnosis, is it?
No, it's actually right after the vehicle is fixed. Rolandus calls this the happy ending trap.
The happy ending trap, I like that.
Yeah, it happens during commissioning when you are bringing the car back online. I mean, you've done the grueling diagnostic work, the physical repair is finished, and there's this massive psychological release of tension.
You just want to declare victory, pack up, and go home.
Right. And in that rush to the finish line, technicians make simple but deadly mistakes. They remove their lockout padlocks early.
Or they forget to collect their conductive metal tools from inside the chassis.
Exactly. They leave high-voltage hazard labels attached, or they fail to communicate with the safety-responsible person in the workshop. The job isn't actually complete until the system is safely re-energized.
And all the administrative safety protocols are closed out. which really boils down to Rolandas's golden rule for the whole process.
Yeah. If you are just a little unsure, take a step back, verify, and continue with confidence. Otherwise, reassess the risks and start over.
Just taking a single step back to break that autopilot mindset, it's literally the barrier between a safe repair and a fatal shock.
Absolutely.
Well, we'll leave you with this final thought. If the happy ending trap is so dangerous in electromobility, where else in your own high-stakes projects are you rushing the finish line and skipping the final crucial checks?